Concepts of percent yield and limiting reactants are very important in industrial applications. If your business is to make sodium hydroxide, you're going to be concerned with how much of my ingredients am I wasting, and what is my efficiency, what's my percent yield. And when you're making a substance, you can often choose which is the limiting reactant. And a lot of times they'll choose the more expensive ingredient to be the limiting reactant and make sure that that gets all used up, make the best use of the expensive ingredient, and then we won't worry so much about the rest. So like if you're making blueberry pancakes, well, the blueberries are probably the most expensive ingredient. And so you're going to want to use up all the blueberries, but you want to make sure you have plenty of other things, the bread. You don't use bread to make pancakes. The flour and the eggs and stuff. You want to make sure you have plenty of that, and so that you can make use of all the blueberries. Another way they choose is sometimes one of the reactants is difficult to remove from the product. Because unlike pancakes, making pancakes, when you put things together in a reaction, they all get mixed up together. And at the end, you have your product in the same container with your leftover reactants. So if you have something that's difficult to remove, that might also be something that they'll make limiting so that it isn't present at the end. So moles are all nice and everything, but we actually use grams. And so we need to be able to calculate limiting reactants and theoretical yields using masses instead of moles. So this is the same idea, but now we're going to put those step at the beginning and a step at the end. And so we're just going to combine some stuff together. So let's just kind of look at a big picture before we do an example. So here we've got sodium and chlorine reacting to form sodium chloride. And we are told that we have 53.2 grams of sodium and 65.8 grams of chlorine, and we're asked to find the limiting reactant and the theoretical yield. Same idea that we've been working with, except it's in grams. So we're going to do two calculations, but this time it's the full-blown grams to moles to moles to grams. First for the sodium, and then for the chlorine. Grams to moles to moles to grams. We're going to end up at the same compound, whatever the product is that we're interested in. And then we're going to identify which one is the smallest. So here's that all set up. 53 grams, and notice how all the units are canceling out so nicely. This would make 135 grams of sodium chloride, and this amount of chlorine would make 108. 108 is smaller, so this is the theoretical yield. The reactant that made that is the limiting reactant. Now there's a mistake in this slide, which I probably should have fixed this morning, but I didn't. There's something missing in the given. And we have to tell you what the actual yield is. The actual yield is 86.4 grams. So given 53.2 grams of sodium, 65.8 grams of chlorine, and an actual yield is 86.4 grams, calculate the percent yield. We've already calculated the theoretical yield. Bless you. So the theoretical yield that we calculated on the previous slide goes in the bottom, 108. This actual yield is just handed to us. And so we take 86.4 divided by 108, multiply by 100%, and we get 80%. So the percent yield is 80%. That means that if you set out to make 100 grams, you would actually make 80 grams. So if you want to make 100 grams, you'd have to do a little calculation and say, well, I know I'm going to lose 20%, so I have to make more, start out making more. And, like with pancakes, if it was really, really important that you have 15 pancakes, then you might actually set out to make 20, right? Just in case something happens to some of them. So let's do an example. Ammonia can be synthesized by the reaction hydrogen and nitrogen reacting to form ammonia. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? So I'm going to take those numbers that I'm given, those masses, I'm going to write them under the balanced chemical equation. So 25.2 grams of nitrogen and 8.42 grams of hydrogen. And they're asking for ammonia. Maximum amount, it's pretty reasonable to assume that they're looking for a mass in grams. So we look at this problem. It doesn't say anything about what's the limiting reactant, right? There's nothing in the words that yells limiting reactant. This is a limiting reactant problem because they give you masses of 2 reactants. And you can't just add them together or do something simple like that. That'd be nice, but it just doesn't work that way. We have to do 2 calculations. So we're going to go grams to moles to moles to grams for each reactant, and we're going to calculate 2 values for the mass of ammonia. And we're going to see which one is smaller, and that will be our answer. So 8.42 grams of hydrogen. Grams to moles. So moles of hydrogen. Grams to moles, so moles of the other thing. Grams to moles to grams. That was a big yawn. It's okay. So that's our path across the top, grams to moles to grams. Previous unit comes into the bottom so that they can cancel out. All of our units are in place. Now we look for numbers. Middle one is the easiest one. Do it first. Moles of ammonia. Well, there's a 2 in front of ammonia, so I need 2 in front of moles of ammonia in my, it's not even close to a 2. And in front of hydrogen is the number 3, so then I put the 3 in there. It's really just that easy. Here I've got NH3. I find that in the formula. Whatever number is in front of it, I write it in front here. There's no switching or matching or anything. You just copy the number down. The first term and the last term are molar masses. I'm going to calculate those up at the top because I need space down at the bottom for another reaction, another equation. So 2 times the mass of hydrogen gives us a molar mass for hydrogen of 2.016. So 1 mole of hydrogen weighs 2.016 grams. And for ammonia, I've got 1 nitrogen and 3 hydrogens. And that's going to end up being 17.034. One mole weighs that much. So that's something that we learned to do this afternoon, that calculation. What's different about this problem is that we recognize we have to do it twice. So I'm going to go ahead and calculate that and write down the answer. 8.42 divided by 2.016 times 2 divided by 3 times 17.034. How many significant figures should I put in this answer? 3. 8.42 was the mass that I was given. 47.4. and that is grams of ammonia. So that's one. Now I'm going to do the other one. 25.2 grams of nitrogen. Again, grams to moles to moles to grams. Write it out if you need to. So grams of nitrogen to moles of nitrogen. Grams to moles, moles of the other thing, moles of ammonia. We're going to the same place. Sometimes students start and they end up calculating grams of hydrogen or something. We're calculating mass of product for both of these. And this will be grams of ammonia. Then we fill in the units on the bottom to cancel out. Let's do that middle one first. We need moles of ammonia. We go to the equation. 2 moles of ammonia. Moles of nitrogen? 1. The last term, we're kind of getting a buy one, get one free thing here. That's exactly the same, isn't it? Grams of ammonia to moles of ammonia. So we don't have to calculate that mass again. So that's like the one little tidbit that you get out of it. 17.034. So that guy ends up being the same. Then we need to calculate the mass of nitrogen, and 2, so that's 2 times 14.01, which is 28.02. That goes in here, 28.02. 25.2 divided by 28.02 times 2 times 17.034 equals 30.6 grams of ammonia. So we did all that hard work. Don't forget to finish. We have to choose one of those. It's the smaller one. This is the amount that can be synthesized if everything goes perfectly. It doesn't ask for the limiting reactant, but what is the limiting reactant? It's nitrogen. Any questions? Here's another one. What, no cheering? Here's the reaction used to obtain iron from iron ore. Fe2O3 plus 3CO forms 2Fe plus 3CO2. The reaction of 185 grams of iron 3 oxide with 95.3 grams of carbon monoxide produces 87.4 grams of iron. Find the limiting reactant, the theoretical yield, and the percent yield. Oh my goodness, right? It's fine. It'll be fine. So if this is like, on the computer screen, then you would write down the equation, the balanced chemical equation, on your paper, and then use that to organize your information. So here I've got 185 grams of that guy and 95.3 grams of this guy and 87.4 grams of that guy. What's different so far? We've got 3 numbers, right? Okay, so we can figure this out. They're asking for the limiting reactant, the theoretical yield, the percent yield. What's the percent yield? Percent yield equals the actual yield divided by the theoretical yield times 100. They had to give us the actual yield. This guy right here, That's the actual yield. You might look at this at first and say, well, why do we need to calculate the theoretical yield? They told me how much iron was made. That's how much was actually made. That's the actual yield. We need to calculate the theoretical yield. So that's a whole big process we just did in the previous example. So we're going to take the 185 grams of iron, Fe2O3, grams to moles to moles to grams. Grams to moles to moles of iron. Gotta zoom out a little bit, I'm writing too tiny here. To grams. Grams to moles to moles to grams. Moles of iron on the bottom to cancel those guys. Moles of Fe2O3 to cancel those guys. And grams of Fe2O3. Again, the middle one is the easiest. So we find Fe in the equation, there's a 2 in front of it. So we're going to put a 2 in front of it down here. We find Fe2O3 in the balanced chemical equation, there's a 1 implied, and so we'll put a 1 in there. This time the last molar mass is the easiest one, right? Because it's an element. We can just read it off the periodic table. We don't have to calculate. 55.85. But we do need to calculate the molar mass for the Fe2O3. I'm going to do that up on the top. So 2 times the mass of the iron plus 3 times the mass of oxygen equals 2 times 5.85 plus 3 times 16, 159.7. So 159.7. 1 mole of iron 3 oxide weighs 159.7 grams. So we got all of our units in there, we've got all of our numbers in there, now we can calculate the answer. 185 divided by 159.7 times 2 times 55.85. And that should have 3 significant figures. And so I come up with 129 grams of iron. That's more than the actual yield, isn't it? And that's generally what we expect, that the theoretical yield is going to be more. So that's half of it. Now we have to take the other one, the carbon monoxide, 95.3 grams of carbon monoxide. Grams to moles to moles to grams. Grams of carbon monoxide to moles of carbon monoxide. To moles of product, here it's Fe, to grams of product. Grams to moles to moles to grams. You think you can remember that? Grams to moles to moles to grams. You can't do moles to grams to grams to moles. It doesn't work that way. We fix our units up. Ugh. And moles of CO down there, and moles of Fe down here. So those cancel, And these cancel and those cancel. The middle one, what's in front of Fe? It's 2. And in front of carbon monoxide is a 3. So that goes down here. This guy right down here. These numbers come from the equation here. The last term is going to be the same, 55.85. Then the first term, we need to calculate the molar mass of carbon monoxide. At least that one's pretty small. Carbon is 12.01 and oxygen is 16. And so that should end up being 28.01. 28.01. 95.3 divided by 28.01 times 2 divided by 3 times 55.85 equals. For 3 sig figs, this rounds to 127 grams of iron. So which one is my theoretical yield? Not the 129. 127. It's the smaller. Right, we think well, theoretical, that's the maximum, right? But it's the maximum given these amounts that we have. And so when you reach the smallest one, that's when one of the reactants has run out. So it stops. So it's the smaller one. That seems a little counterintuitive to some types of brains. And so you just need to think about it and work around until it makes sense to you. That's the theoretical yield. It's asking for a limiting reactant, so that's this guy over here, carbon monoxide, Lr. And now we have the information we need to calculate the percent yield. The actual yield was given to us, and it will always be given to you unless we are actually doing an experiment. So 87.4 grams, we just calculated the theoretical yield. Notice that these units cancel out, times 100%. The unit on a percentage is percent, nothing else. 87.4 divided by 127 and multiply that by 100. Both of our masses here had 3 sig figs, so we're going to express our percentages as 68.8%. That's our percent yield. Any questions? That's sort of a problem. This one right here, that's the biggest problem. Because here we've got the limiting reactant, and we have to calculate the percent yield, the theoretical yield, and then they also want the percent yield on top of that. So that's a lot of stuff all rolled up in one. Question?
How do you know the iron is the actual yield? Because it's after the right after the arrow.
How do I know that this guy right here is the actual yield? It's a very good question. So in the description, in the question, it says the reaction of 185 grams of this and 95.3 grams of CO produces 87.4 grams. Now, they're not real obvious about it, but they're stating that this is how much was made. So you kind of have to be a detective and recognize that's how much is actually being made. Then it says find the limiting reactant, the theoretical yield. When we do these calculations, we come up with numbers that are a lot higher than the 87. And that's because this process doesn't work perfectly. Just like making the pancakes, you know, we burned 3 of them and dropped one on the floor. Stuff happens. Stuff happens in chemistry too, it's just different kinds of stuff. Does that answer your question? It's a good question. Anybody else?